In previous class, we have already talked about the packing efficiency in HCP and CCP structures, and there were some results that you were supposed to remember were 74% for the CCP structure, 68%, 68% was for the HCP structure. Sorry, uh, let me 68% for CCP structure and 52.4 was for HCP structure, and after that we were supposed to study imperfection in solids. So let's just start reading and then I will describe as soon as we read. Although crystalline solids have short range as well as long range order in the arrangement of their constituent particles, yet crystals are not perfect. Usually a solid consists of an aggregate of large number of small crystals. These small crystals have defects in them. This happens when crystallization process occurs at fast or moderate rate. Single crystals are formed when the process of crystallization occurs at extremely slow rate. Even when these crystals are not free of defects. The, the defects are basically irregularities in the arrangement of constituent particles. Broadly speaking, the defects are of two types, namely point defect and line defects. Point defects are the irregularities or deviations from ideal arrangement around a point or an atom in a crystalline substance, where the line defects are the irregularities or deviations from ideal arrangement in entire rows of lattice points. These irregularities are called crystal defects, which will confine our decision to find defects only. So basically, there are some defects that you might find in the solids that are present around us. It is not as ideal situation we study as we have studied before, that you will find an infinite arrangement just like the primitive cell of the solid, infinite times repeating itself in the forward, backward, right side, upside down side. It won't be the real case in the real life. So there might be some defects that you find in the solid structures, and there are two types of that. There might be more different types of, but according to our studies, we have only two types of defects, that are point defect and line defects. And the point defect are ideal arrangement around a point or an atom in a crystalline substance. So the crystalline substance or the crystalline matter, those who arrange ideal arrangement around a point, just like you have one dimensional line structure of the substance that we have studied in the types of arrangement, and there might be some different kind of atom present in the line of that substance or matter, that will be called as point defect. And whereas the line defect are the irregularities or deviation from the ideal arrangement in entire rows of lattice. So the entire row, the entire line, that is the entire 1D, one dimensional line that is making the whole three-dimensional or two-dimensional structure of the matter, is has a total different kind of atoms in it, or there might be some defects, there might be some voids, there might be some unexpected atoms that are not expected to be present over there. So that is called as a line defect. Now we have to study about types of point defects. point defects can be classified into three types: stoichiometry defects, second impurity defects, and third non-stoichiometric defects. First, stoichiometric defects. There are the point defects that do not disturb the stoichiometry of the solid. They are also called intrinsic or thermodynamic defects. Basically, these are two types of vacancy defects and interstitial defects. So the stoichiometry you might remember from the mole concept, that we used to call the number that was placed before the compound while we were balancing the chemical reactions. So these defects that we found here do not disturb the stoichiometry of the solid. Like, what do you mean by the stoichiometry of the solid? The ratio of the number of ions with respect to the other ion. Like NaCl, the number of NaCl particles, Na plus ions and Cl minus ions, will be a ratio. If you take the ratio of both the ions before and after there is defect in the solid, then it will come out as sand. There are also called intrinsic or thermodynamic defects. Intrinsic is a new word. Or thermodynamic defects. Basically, these are of two types: vacancy defects and interstitial defects. First, vacancy defect. When some of the lattice sites are vacant, the crystal is said to have vacancy defect. This results in decrease in density of the substance. This defect can also develop when a substance is heated. So when some of the lattice sites are vacant, the lattice sites or the voids, you can say, the crystal is said to have vacancy defect. Like, if you just remove some of the ions from NaCl, some of Na plus ions are removed, some of Cl minus ions are removed from the lattice, from the solid lattice, then you will get lot of vacancy, or you can say as voids in the lattice, and that can be called as vacancy defect. This results in decrease in density of the substance. Obviously, if there is more gap between the solids, between the atoms, then there will be more vacancy, and the mass or the volume will decrease, and that will decrease the density of the substance. The defect can also develop when the substance is heated. Okay, so the substance, when you heat a substance, what happens is, like, you are basically providing the atoms more energy. Okay, temperature is a form of kinetic energy of the molecules, as you might have studied in thermodynamics. So the vibration or the motion of atoms increases inside the lattice, and that might cause some vacant spaces between the atoms that are present in the lattice, and then you can call it as vacancy defect. Interstitial defect: when some constituent particles, atoms or molecules, occupy an interstitial site. So if you already have some space between your lattice, between the atoms inside your lattice, then some atoms might come in contact with that lattice and might get stuck, or might get attracted electrostatically. Okay, so when some constituent particles occupy an interstitial site, the crystal is said to have interstitial defect. The defect increases the density of the substance. Obviously, there was no. Okay, this is interesting, right? The density increases in the sense of the vacancy defect, including the substance already vacancy defect, then if you add some atoms in the vacant space, then obviously the volume has remained the same and the mass has increased, so density will obviously increase. So we need to keep in mind that we are comparing the density with respect to the vacancy defect lattice rather than the initial or the symmetric lattice that we had been studying. Vacancy and interstitial defect, as explained above, can be shown by non-ionic solid. Ionic solid must always remain or maintain electric neutrality. Example: NaCl. NaCl. If NaCl, if I remove two Na plus ions from the lattice, just two, I just remove two atoms from the lattice of NaCl, then the lattice remain will have overall -2 charge because of the leftover to Cl minus. Those who are not connected or not in contact with the positive charge. So then we have to place a second group, I would say second group metal in his in its charge form, so as to balance or balance the charge, I guess, balance the electrical charge that is introduced in the neutral atom. Okay. Barroso. Vacancy and interstitial sites are explained. Ionic solids must also maintain electric neutrality. Rather than simple vacancy or interstitial defect, they show these defects as Frankel and Scotty defects. Simple vacancy or interstitial defect, they saw these defects as, this is just a different name for these, Frankel and Scotchy defects. I don't know how to pronounce that name. Third, Frankel defect. This defect is shown by ionic solids. The smaller ion, usually cation, is dislocated from its normal site to an interstitial site. It creates a vacancy defect at its original site and an interstitial defect at its new location. Now, the interstitial defect might not be caused by a different anion or cation. Usually, the cation moves because it is smaller in size. So, if we put the same ion, the same cation to a different position where it is not expected to be there, then it is interstitial defect for the new location and vacancy defect for the previous or the native location. So it creates a vacancy defect at its original site and an interstitial defect at its new location. Frankel defect is also called dislocation defect. It does not change the density of the solid because there is no mass loss or the volume loss, anything. Frankel defect is shown by ionic substance in which there is a large difference in the size of ions. For example, ZnS, AgCl, AgBr, and AgI due to small size of Zn plus 2 and Ag plus ions. Frankel defect is shown by ionic substances in which there is a large difference in the size of ions. Usually, the cation is small rather than an anion, so the more the difference between the size of the anion and cation between the lattice changes, there are more chances that the cation have more space to move around, or you can change its location more easily if there is more difference in size. the size of the cation and anion in the lattice itself. So Zn plus 2 and S2 minus. S2 minus sulfur is from the third period and 16th group, and zinc is from fourth period and 12th group. So as we know that as you go down the group, down a single group, the size increases, and as you go left to right, size decreases. Am I right? And if you give some charge or -2, then obviously sulfur in its -2 stage will be as big as argon. Not as big as, but comparatively it will be as big as argon. Same size, I would say, almost same size. And Zn in its +2 form will be much smaller than nickel as well, because the side, I guess, the hold on a second. Yeah, so I think this is a Scotchy defect. It is basically a vacant defect in ionic solids. In order to maintain electric neutrality, the number of missing cations and anions are equal. Okay, this is a special case of the Frankel defect, in which the number of missing cation and anion are the same, because usually in the ionic lattice you have to maintain the electric neutrality of the lattice, so you don't have so many options to do that. So you can remove the same number of anions and cations with respect to their compound, or the oh god, what is that called, with respect to their stoichiometry inside the compound. What you call, if you write down Al2 N3, sorry, there is no compound Al2 N3. If you write Al2 any Al AlCl3 might be. So if you have to put out 3 Cl minus ions and 1 Al3 plus ion, so as to maintain the electric neutrality of the lattice. You know what I mean? You don't have to pull out the same number of anions and cations. That's not the case. That's not how you maintain the electrical neutrality of the solid. So Stokes defect, it is basically a vacant defect in ionic solids. In order to maintain electric neutrality, the number of missing cations and anions are equal. Like simple vacancy defects, Stokes defect also decreases the density of the substance. Number of such defects in ionic solids is quite significant. For example, in NaCl, there are approximately 10 to the power 6 Stokes pairs per centimeter cube at room temperature. In 1 centimeter cube, there are about 10 to the power 22 ions. Thus, there is 1 Stokes defect per 10 to the power 16 ions. Stokes defect is shown by ionic substance in which the cation and anions are of almost similar size. For example, NaCl, KCl, CaCl, and AgBr. It may be noted that AgBr shows both Frankel as well as Stokes defect P. So there are so much defects. There are so much Frankel and Stokes defect In the real life lattice, there are like 10 to the power 22 ions in about only 1 centimeter cube. You can imagine the number that is inside a small piece of solid that you have. It's a quite low. Okay, and it is mostly because of the Stokes effect. Like there could be atoms missing. There is no such symmetry in the real life as we imagine, usually imagine in science. B. Impure effects. If molten NaCl containing a little amount of SrCl2 is crystallized. If molten NaCl, you take molten NaCl, you take NaCl powder from white powder and then you heat it there, that's how you get molten NaCl. And a little amount of SrCl2 is crystallized. Some of the sites of Na plus ions are copied by Sr plus 2. Each Sr plus 2 replaces two Na plus ions. That's how you maintain the electric neutrality of the solid. It occupies the sides of one ion and other side remains vacant. The cationic vacancies thus produced are equal in number to that of Sr plus 2 ions. Another simple example is the solid solution of CdCl2 and AgCl. The molten state NaCl, if molten NaCl containing a little amount of SrCl2 is crystallized. Okay, some of the sites of Na plus are occupied by Sr plus 2. Each Sr2, it occupies the site of one ion and other side remains vacant. The cationic vacancies thus produced are equal in number to that of Sr plus 2 ions. Okay, that means to real well. And another similar example is the solid solution of CdCl2 and AgCl. You might say in the figure 1.27 introduction of cation vacancy in NaCl by substitution of Na plus by Sr plus 2. So you have one vacancy and one Sr plus 2 ion, just because to maintain the electric neutrality of the solid. C. Non-stoichiometric defects. The defects discussed so far do not disturb the stoichiometry of the crystalline substance. However, a large number of non-stoichiometric inorganic solids are known, which contain the constraint elements in non-stoichiometric ratio due to defects in their crystal structures. These defects are of two types. First, metal excess defect, and second, metal deficiency defect. Non-stoichiometric defects. The defects discussed so far do not disturb the stoichiometry, means the stoichiometric ratio of the compound or the ions remains the same if you write down the formula of the compound. Whereas now we are about to study where the compound formula changes, that is non-stoichiometric defects. However, a large number of non-stoichiometric inorganic solids are known, which contain the constraint elements in non-stoichiometric ratio due to defects in the crystal structures. These defects are of types. Metal excess defect, in which the metal, just by judging the name, in which the metal is taken in excess, is not taken in excess but becomes more rich in the lattice, and the anion numbers usually decreases. Not usually decreases, simply decreases, because relatively decreases. That's what I wanted to say. It relatively decreases as the metal. My microphone. As the metal increases, the metal part or the metal ions increase, the anion part decreases with respect to metals. Second, metal deficiency defect. So we don't usually define deficiency with respect to anion because it is much bigger in size and it is more difficult to move out or move elsewhere. So you can't have deficiency or excess of anion usually. So we define with respect to the cation where you can imagine it to be moving around, same as the situation that we have imagined in atomic structure where you always imagine electrons to be moving around rather than yeah, rather than uh, protons because of their bigger mass, more mass. Okay, first metal assist defect. Metal assist defect due to anionic vacancies. Alkali halides like NaCl and KCl shows this type of defect. When crystals of NaCl are heated in an atmosphere of solid sodium vapor, the sodium atoms are deposited on the surface of the crystal. The Cl minus ion diffuse to the surface of the crystal and combine with Na atoms to give NaCl. This happens by the loss of electron by sodium atoms to form Na plus ions. The released electrons diffuse into the crystal and occupy anionic sites. As a result, the crystal now has an excess of sodium. The anionic site occupied by unpaired electrons are called F centers, from the German word Farbenzender, Farbenzender for color center. They impart yellow color to the crystal of NaCl. The color results by excitation of these electrons when they absorbs energy from visible light falling on the crystals. Similarly, excess of lithium makes LiCl crystals pink and excess of potassium makes KCl crystal violet or lilac. Okay, so the metal acid effect due to anion vacancies. Anion vacancies. Alkyl halide like NaCl and KCl show this kind of defect. When crystals of NaCl are heated in an atmosphere of sodium vapor, the sodium atoms are deposited on the surface of the crystal. The Cl minus ion diffuses to the surface of the crystal and combined with Na atoms to give NaCl. This happens by loss of electron by sodium atoms to form Na plus ions. The released electrons diffuse into the crystal and occupy anionic sites. So this is really going complex. Okay. Now, if you think about it, when you heat a crystal in atmosphere of solid sodium, like if you take sodium paper inside a jar, closed jar, and heat NaCl that is in the bottom of it, then the Cl minus ion diffuse to the surface of the crystal because there is sodium outside the solid that is of the NaCl. So Cl minus goes to the surface so as to react with Na, and Na becomes Na plus and releasing one electron that is then which then makes a vacancy inside the lattice of the solid, and that's why F centers are formed from the German word Farbenzender, Farbenzender, Farbenzender. I don't know how you pronounce that name, but German people are really smart. I know that much. Metal oxides defect due to the presence of extra cations at interstitial sites. Zinc oxide is white in color at room temperature. On heating, it loses oxygen and turns yellow. Okay, zinc is a white powder. Zinc oxide is white. Sorry, zinc is not white. Zinc oxide is white in color at room temperature. On heating, it loses oxygen and turns yellow. You need to remember that Zn plus 2 is yellow in color. So if you heat ZnO, heating gives Zn plus 2 plus half or 2 plus 2 electrons. Now these two electrons will form F centers, Farbenzon centers, okay? And that will give a color to the lattice because F centers gives color, and mostly we have seen in the the crystalline structures or the coordinate compounds where you get color when usually you get color when you have unpaired electrons. So there is unpaired electron in between the lattice, and that's why you will probably get a color center over there. Whenever there is F center, it is also a color center. Now there is an excess of zinc in the crystal, and its formula becomes Zn1 plus XO. The excess of Zn plus 2 ions move to the interstitial sites and electrons to the neighboring interstitial sites. Metal deficiency defect. There are many solids which are difficult to prepare in the stoichiometric composition and contain less amount of the metal as compared to the stoichiometric proportion. A typical example of this type is FeO, which is mostly found in the with the composition of Fe 0.950. It may actually range from 0.930 to Fe 0.960. In crystals of FeO, some Fe plus 2 cations are missing, and the loss of positive charge is made up by presence of required number of Fe plus 3 ions. So first we had metal excess defect, and now we are studying about the metal deficiency defect. So usually in crystals like FeO, the Fe plus 2 ions get missing, and loss of positive charge is made up by the presence of the required number of Fe plus 3 ion. So F plus 2 part in the lattice goes missing, and to maintain the electric neutrality of the lattice, we introduce Fe plus 3 ion. So Fe plus 3 ion, Fe plus 3 ion increases, but the Fe, number of Fe that we are counting as overall in the structure will be indicated as Fe and will decrease from the formula of FeO. 1.10 electrical properties. Solid exhibit an solids exhibit an amazing range of electric conductivities, extending over 27 order of magnitude, ranging from 10 to the power minus 20 to 10 to the power 7 ohm per ohm inverse meter inverse. Solids can be classified into three types on the basis of their conductivities. Conductors, the solid with conductivities ranging between 10 to the power 4 to 10 to the power 7 ohm Ohm inverse, meter inverse are called conductors. Metal have conductivities in the order of 10 to the power 7 ohm. Meter for inverse are good conductors. So 10 to the power ohm inverse, meter inverse is a really good conductivity of a substance, and you can call them as conductors. Second, insulator. These are the solids with very low conductivities ranging between 10 to the power minus 20 to 10 to the power minus 10 ohm inverse, meter inverse. Now we have insulators. Those are the substances which do not conduct electricity and have very low conductivities. Semiconductors are those solids with conductivity in the intermediate range from 10 to the power minus 6 to 10 to the power 4. It can act as conductor in some cases and can act as insulator in some cases. Conduction of electricity or in metals. A conductor may conduct electricity through movement of electrons or ions. Metallic conductors belong to the former category and electrolytes to the latter. Metals conduct electricity in solid as well as molten states. The conductivity of metal depends upon the number of valence electrons available per atom. Metals conduct electricity in solid as well as molten state. It doesn't matter if you take metals in their molten or solid state, they will act as conductors. The conductivity of metal depends upon the number of valence electrons available per atom. The atomic orbital of metal form molecular orbits, which are so close in energy to each other as to form a band. If this band is partially filled or it overlaps with a higher energy occupied conduction band, then electrons can flow easily under an applied electric field, and the metal shows conductivity. The gap between filled valence band and the next higher unoccupied band, conduction band, is large. Electron cannot jump to it, and such a substance has very small conductivity and it behaves as an insulator. So basically, if you have more free electrons, then the electrons carry charge. We know that, and electron carrying charge per unit time is electricity. Sorry, current, and current means electricity. It doesn't mean electricity can. It's not the same thing. Current is not equal to electricity, but that's how you find out there is conduction or there is supply of charge. There is charge moving from one point to another. Then it is having conduction, or the compound that we use is conductor and electron are conducting, or the compound is conducting electricity. Conduction of electricity in semiconductors. In case of semiconductor, the gap between the valence bond and conduction band is small. Therefore, some electrons may jump to the conduction band and show some conductivity. Electrical conductivity of semiconductors increase with rise in temperature. Since more electron can jump to the conduction band, substances like silicon and germanium show this kind of behavior and are called intrinsic semiconductors. The conductivity of these intrinsic semiconductors is too low to be of practical use. Their conductivity is increased by adding an appropriate amount of suitable impurity. This process is called doping, and itself it says dope. So this process is called doping, and this is really smart how they do it. The conductivity of these intrinsic semiconductor is too low to be practical use. You can't use some of the semiconductors, like every semiconductor you can't use for home electricity or any kind of purpose, but they may be used for different purpose. Like you don't always require conductors it doesn't mean like there are some conductors and there are some insulators and semiconductors. So best is conductors. You require insulators as well to build the whole home supply of the electricity to run in a way that is more human friendly, I would say. The conductor of these intrinsic intrinsic semiconductor is too low to be of practical use. Their conductivity is increased by adding an appropriate amount of suitable impurity. This process is called doping. Now, now if you look at the figure 1.29, distinction among metal, insulator, and semiconductors. In each case, an unshaded area represents a conduction band. Partially filled band energy, we are finding out the energy. So partially filled band, overlapping band, and this is metals and insulators, conduction band, implement, forbidden zone, large energy gap, filled band, and semiconductor. It is small energy gap, but there is energy gap. In metal, there is no energy gap, so the electrons go to the conduction band or the conducting area where the electron can move and conduct electricity, whereas in insulator there is too much gap between the conduction and non-conduction band or the filled band, so there is large energy gap and electron can jump, or the energy not that much high in the electron so it can conduct electricity. And in semiconductor is the small energy gap between there, so it depends upon the energy of the electron whether it will be able to close the small energy gap or not. Now continue back on doping. Doping can be done with an impurity which is electron rich or electron deficient as compared to the intrinsic semiconductor, silicon or germanium. So intrinsic semiconductor, silicon or germanium. So in silicon Si and germanium Ge are only the two semiconductors which are intrinsic. Such impurities introduce electronic defects in them. A. Electron rich impurities. Silicon and germanium belong to 14 of the periodic table and have 4 valence electrons each. In their crystal, each atom forms 4 covalent bonds and its neighbors. When doped with a group 15 element like P or As, which contain 5 valence electrons, they occupy some of the lattice sites in silicon or germanium crystal. 4 out of 5 electrons are used in the formation of 4 covalent bonds with the 4 neighboring silicon atoms. The 5th electron is extra and becomes delocalized. These delocalized electrons increase the conductivity of doping silicon. Here the increase in conductivity is due to negative charge electron. Here silicon doped with electron rich impurity is called N-type semiconductor. Okay, so electron rich impurities where you add a kind of atom which have more valence electron than the present intrinsic semiconductor, then it will make the lattice or substance more electron rich. The substance is impure, by the presence of the another atom, but it is electrically more rich, or it has more electrons than the original compound. So it is called electron rich impurities. And talking about the electron deficient impurities, silicon or germanium can also be doped with a group 13 element like B, Al or Ga, which contains only 3 valence electrons The place where the fourth valence electron is missing is called electron hole or electron vacancy. An electron from a neighboring atom can come and fill the electron hole, but in doping it is so it would leave an electron hole at its original position. If it if it happens, it would appear as if the electron hole had moved in the direction opposite to that of electron that filled it. Under the influence of electric field, electron would move towards the positive charge plate through electronic holes, but it would appear as if electron hole are positively charged and are moving towards negatively charged plate. This type of semiconductor are called p-type semiconductors. So if you have n-type, then that semiconductor have more electrons than the p type semiconductors, and then you have neutral semiconductors. Hmm. That's how you find out. Now you have some figures. Silicon atom. So there is the perfect crystal that you see in the A part, and then you have N type where you increase the number of electrons because AS has more number of electrons than the silicon, so it would increase the number of mobile electrons. And then you add boron-like compound where the number of mobile electrons are less than the original perfect crystal. Then it is called the p-type semiconductor. Figure 1.3. Creation of n-type and p-type semiconductors by doping 13 and 15 element group. Application of n-type and p-type semiconductors. Various combinations of n-type and p-type semiconductor are used for making electronic components. Diode is a combination of n-type and p-type semiconductors and is used as a rectifier. Transistors are made by sandwiching layer of one type of semiconductor between two layers of the other type of semiconductor. NPN and PNP type of transistors are used to detect or amplify radio or audio signals. The solar cell is an efficient photodiode. You ever see a solar cell in the solar pan? That is an efficient photodiode. And photodiode are made using a PNP or NPN type of transistor. So the solar cell is an efficient photodiode used for conversion of light energy into electrical energy. Germanium and silicon are group 14 element and therefore have a characteristic valence of 4 and form 4 bonds as in diamond. A large variety of solid state material have been prepared by combination of 13 and 15 or 12 and 16 to stimulate average valence of 4 as in germanium or silicon. Typical compounds of group 13 and 15 are INSB, ALP, aluminum phosphate, and gallium arsenate. Gallium arsenate GaAs semiconductor have very fast response and have revolutionized the design of semiconductor devices. ZNS, CDS, CDSE, and SGTE are examples of group 12-16 compounds. In these compounds, the bonds are not perfectly covalent and the ionic character depend upon the electronegativity of the two elements. It is interesting to learn that transition metals oxides show marked difference in electrical properties. TiO, CrO2, and ReO3 behave like metals. Rhenium oxide (ReO3) is like metallic copper in its conductivity and appearance. Certain other oxides like VO2, VO3, and TiO3 shows metallic or insulating properties depending on temperature. Now moving on to the next section, magnetic properties. Every substance has some magnetic property associated with it. The origin of these properties lies in the electrons. Each electron is an atom behave like a tiny magnet. Its magnetic moment originates from two types of motions. A, or the first, its orbital motion around the nucleus. Second, its spin around its own axis. Electron, being a charged particle and undergoing these motions, can be considered as a small loop of current which possesses a magnetic moment. Thus, each electron has a permanent spin and an orbital magnet moment associated with it. Magnitude of this magnetic moment is very small and is measured in the unit called Bohr magneton, mu b. It is equal to 9.27 into 10 to the power minus 24 ampere meter square. On the basis of their magnetic properties, substance can be classified into five categories. First, paramagnetic; second, diamagnetic; third, ferromagnetic; fourth, antiferromagnetic; and fifth, ferrimagnetic. First, paramagnetic. Paramagnetic substances are weakly attracted by a magnetic field. They are magnetized in a magnetic field in the same direction. They lose their magnetism in the absence of their magnetic field. Paramagnetism is due to presence of one or more unpaired electrons which are attracted by the magnetic field. O2, Cu plus 2, Fe plus 3, Cr plus 3 are some examples of these substances. Second, diamagnetism. Diamagnetic substances are weakly repelled by a magnetic field. H2O, NaCl, and C6H6 or benzene are some examples of such substances. These are weakly magnetized in a magnetic field in opposite direction. Magnetism. Dimagnetism is shown by those substances in which all the electrons are paired and there are non-paired electrons. Pairing of electrons cancels their magnetic property and they lose their magnetic character. Ferromagnetism. A few substances like iron, copper, nickel, gadolinium, and CrO2 are attracted by very strongly by a magnetic field. Such substances are called ferromagnetic substances. Besides strong attractions, these substances can be permanently magnetized. In solid state, the metal ions of ferromagnetic substances are grouped together into small regions called domains. Thus, each domain acts as a tiny magnet in an unmagnetized piece of a ferromagnetic substance. The domains are randomly oriented and their magnetic moment get cancelled. When the substance is placed in a magnetic field, all the domains get oriented in the direction of the magnetic field, and a strong magnetic effect is produced. This ordering of domain persists even when the magnetic field is moved and the ferromagnetic substance becomes a permanent magnet. For antiferromagnetic substances like MnO showing antiferromagnetism have domain structures similar to ferromagnetic substances, but their domains are oppositely oriented and cancel out each other's magnetic moment. Ferrimagnetism. Ferrimagnetism is observed when the magnetic moment of the domains in a substance are aligned in parallel and anti-parallel directions in unequal numbers. They are greatly attracted by magnetic field as compared to ferrimagnetic substances. FeO4 magnetite. Fe- Ferrites like MgFe2O4 and ZnFe2O4 are examples of such substances. These substances also lose ferromagnetism on heating and become paramagnetic. Figure 1.32. Symmetric alignment of magnetic moments in ferromagnetic, antiferromagnetic, and perimagnetic. So in ferromagnetic, you get only one directional magnetic moments or uniform magnetic moment, and whereas in antiferromagnetic you get alternatively upward and downward direction of the magnetic moment, and in ferromagnetic you get different kind of, you can judge like ferromagnetism is observed when the magnetic moment of the domain in the substance are aligned in parallel and anti-parallel direction in unequal numbers. They should not be anti-ferromagnetic because they will become anti-ferromagnetic then, but the unequal numbers should be there so you get a specific direction for magnetic field. Then there are some questions and there is summary. I would like to read the summary for this chapter. Solid have definite mass, volume, and shape. Let me just get a sip of water. Solid have definite mass, volume, and shape. Let me turn off the fan as well because summary. Solid have definite mass, volume, and shape. This is due to the fixed position of their constituent particles, so distance, and so strong interactions between them. In amorphous solids, the arrangement of constituent particles has only short range order, and consequently they behave like super-cooled liquids. They don't have sharp melting points and are isotropic in nature. In crystalline solids, there is a long range order in the arrangement of their constituent particles. They have sharp melting points, are anisotropic in nature, and their particles have characteristic shapes. Properties of crystalline solid depend upon their nature of interactions between their constituent particles on their base on the species. They can be divided into four categories named molecular, ionic, metallic, and covalent solids. They differ widely in their properties. The constituent particles in crystalline solid are arranged in a regular pattern which extends through the crystal. This arrangement is often depicted in the form of a three-dimensional array of points, which is called crystal lattice. Each lattice point gives the location of one particle in space. In all 14 different types of lattice are possible, which are called Bravais lattice. Each lattice can be generated by repeating its by repeating a small characteristic portion called unit cell. A unit cell is characterized by its edge, length, and three angles between these edges. Unit cell can be either primitive, which have particles only at their corner positions, or centered. The centered unit cell have additional particles at the body centered, at the center of each face centered, or at the center of two possible faces, hand centered. These are seven types of primitive cells, taking centered unit cells also into account. There are 14 types of unit cells in all, which result in 14 Bravais lattice. Close packing of particles result into highly efficient lattice. Hexagonal close packing (HCP) and closed packed cubic closed packed (CCP). Later is also called face-centered cubic (FCC). In both of these packings, 74% space is filled. The remaining space is present in the form of two types of voids, octahedral void and tetrahedral void. Other types of packing are not closed packing and have less efficient packing of particles, while in body-centered cubic lattice (PCC), 68% space is filled. In simple cubic lattice, only 52.4% space is filled. Solid are not perfect in structure. There are different types of imperfections or defects in them. Point defects and line defects are common types of defects. Point defects are of three types: stoichiometric defect, impurity defect, and non-stoichiometric defect. Vacancy defect and interstitial defect are the two types of basic types of stoichiometric point defects. In ionic solid, these defects are present as Frenkel and Stokes defects. Impurity defects are caused by the presence of an impurity in the crystal. In ionic solids, when the ionic impurity has a different valence than the main compound, some vacancies are created. Non-stoichiometric defects are of metal excess type and metal deficient type. Sometimes calculated amounts of impurities are introduced by doping in semiconductors that change their electrical properties. Such materials are widely used in electronic industries. Solids show many types of magnetic properties like paramagnetism, diamagnetism, ferromagnetism, antiferromagnetism, and ferrimagnetism. These properties are used in audio, video, and other recording devices. All these properties can be correlated with their electronic configurations or structures. So that was the summary, and we won't be doing these questions. I might do after all the reading is done, but we will continue with the solutions in the next class.